Continuing with section 3 of this chapter, we're going to be looking at functions here. Functions, previously we've limited that to polynomial functions, linear or quadratic. We're going to extend that into higher degree polynomials. Later in the quarter, we'll be extending that to things that are not polynomials. So let's look back in general at what a function is. If you have two things and you somehow describe a relationship between them in some way, that's a relation. A function is just a relation that has a particular restriction. The restriction is that for any input into the function, there's one and only one output. That way you don't get into the question of, well, is it this answer or is it this answer? Remember on the circle that we had a few minutes ago? For a value of x, do I get this number or do I get this number? A circle is not a function because it's ambiguous. A function has to be completely defined with no ambiguity. In a function, or in a relation either, the domain are the values that you put into it. That's called the independent variable. A function has, two pieces. There's a piece you put in and a piece that comes out as a result of calculating the function. The piece you put in is known as the independent variable. The piece you get out is the dependent variable. The domain, these independent points or independent values, can be limited by either mathematics or by the problem. In other words, the values we're allowed to put into this function or into this relation may be restricted. I cannot put a value in which will cause me to divide by 0. That's a mathematical limitation. A problem limitation would be something like, I cannot put in a negative length for a side of a rectangle because there's no such thing. Mathematically, a negative number is completely fine. But in a problem, there are limitations. You can't have negative time. You can't manufacture fractions of an item. You have to you either manufacture the whole thing or you don't manufacture it. So problems can also limit what values are allowed. So there are two forms of restriction on the input values, on the domain. Range is when you plug in all of these allowed values for the independent variable, what values will come out as the dependent variable. That's what the range is that group of values that come out of plugging in all of the independent variables. The range depends on what you put in as well as on the form. So you could be limited by mathematics. You cannot put anything in that would, the form can't be such that it would cause a division by 0. And you can't have an output that would give you a something like a negative time. So you're limited both on the input and on the output. The output is limited in addition by what values are allowed to be put in. So for a relation to be a function, each value of the independent variable has one and only one value out, the dependent variable. So if I give you an input value, everybody will get the same output. There's no ambiguity about which one it is. That's the limitation that a function places on a relation. Now, you may have two different inputs wind up giving you the same output. So I could plug x equals 5 in and get 25 for an answer. I could plug x equals minus 5 in and also get 25 for an answer. That's the squared function. Two different inputs that give the same output. That's still a function, because for any input, there's no question what the output is. And that's the requirement on function. Later we're going to see something called one-to-one, which is going to put a requirement on the reverse. But for now, we're just limiting what values the input has. I'm sorry, what values the output has. The output has to be unique. An easy way to see this is when you draw the arrow diagrams. You can think of a function as having inputs and outputs. All of the possible values for the input are the domain. All the possible values for the output is the range. And so the function is what relates this to this. If you have every value in that, if each value in your input is connected to only one value of the output, and every one of them is different, so 2 to 3, 5 to 4, etc., there is no common thing. Every arrow there's only one arrow coming out of anything, and every arrow ends in only one place. There's not two lines from any one of these numbers. That is a function. That's the perfect case where there's nothing overlapping. Now, here, this one goes to a single value, this one goes to a single value, but here, if I put 8 in, what's the answer? Not sure. This is not a function. Over here, that one goes to there, this one goes to there, this one goes to 6, this one also goes to 6. That's okay, because no matter what value I put in, there's no question what my output is going to be. Here, there was a question. When I put 8 in, I don't know for sure what my output is. Here, if I put in 4, I know what my output is going to be. No question. If I put in a 2, I know what my output is. No question. So those are the distinctions between functions and just relations. That middle one still has a domain. It still has a range. It's just not a function because it doesn't have that uniqueness. If we want to determine whether we have a relation or a function, depending on what form your relation is given in, you use different techniques. One way to write a relation is by a set, and each element in the set is an ordered pair. So you have a set of ordered pairs. The first number in your ordered pair is the input, the independent variable. The second one is the dependent variable. So if you have this set of ordered pairs, which forms a relation, the way to check that type of relation is to look at your first elements. Look at every first element in the pairs. Does anything repeat? If nothing repeats, then it's a function. But you have to do a second test. What if they do repeat? If they don't repeat, it's a function, you're finished. But if you do repeat, it's still possible to be a function, but only if, when a first element repeats, the second elements are the same. If the first element repeats and the second element does not repeat, then it's not a function. So it depends on what you do when you check. Here's an example. Here is a set of ordered pairs. You know, the braces here are set notation. Here are my ordered pairs. If we want to see if this is a function, it's definitely a relation, because by definition a set of ordered pairs is a relation. what I should do is look at these first elements, -4, 0, 2, and -4. If I have no repetition, it's a function. But I have repetition here, don't I? I have a -4 there, I have a -4 there. So I have repetition. So on those two pairs, what I need to do is look at the second elements. If my second elements are the same, it's a function. If they're not the same, it's not a function. So I have -4 and -4, so I check the second elements. They're not the same number. That is not a function. So it's a simple test. In this one, check your first elements. Well, I do have a repeated one, right? The 3 is repeated. So check my second ones. Well, the 1 is the same in both cases. That's okay. That is a function. So very simple when you have sets of ordered pairs. There's also another simple type of function to test. That's when you have a graph of the function. Or I should say a graph of the relation. The way to test a graph is to use the vertical line test. You draw a vertical line through the graph. If that vertical line touches the graph in more than one place, it's not a function. If you can find any place on that graph where a vertical line will touch it in more than one place, it is not a function. Now, you have to be realistic in where you're drawing the line. You can't draw the line out where the function doesn't exist. That doesn't make sense because it's not there at all. So you only draw it where the graph exists. And if it touches more than once, if you can find a place. I mean, most relations, you can find a place where it only touches once, but that's not the point. The point is, can you find any place where it touches more than once? So here's an example. Is that a function? Well, I draw a vertical line there, it's okay, there it's okay, there it's okay, and so forth. Okay, okay, okay. Everywhere I draw that, I only touch the graph in one place. So it's a function. So a vertical line test is really an easy one. One way to think about doing this is when you're looking at your graph here, visualize a vertical line kind of scanning across here. And is there any place it's going to wind up touching the graph more than once? Make sure it's a vertical line. What about this one? If I drew a line right here, it doesn't make any sense, so don't draw it there. If I draw it right there, it's only touching in one point. But the thing says, can I draw it anywhere that it touches? Well, I can draw it out there and it touches twice. Therefore, that is not a function. I only have to find one thing, one place to make it not a function. Okay, so what's the domain of this relation? Remember, domain is that group of inputs. What are my inputs on ordered pairs? The first ones. So what's the domain of this function, of this relation? And the range? Okay, so that's the domain and range. Very easy. Is it a function? Doesn't repeat means is a function. Doesn't repeat means it is a function. If it repeats, then you have to have the same or it's not a function. So Just looking at the first, if none of the first repeat, it is a function, because you don't run the risk of an input going to two different outputs if you only have one place that you put it in. You can also have relations in a table form. That's a form of a relation. You have x's are the inputs, y's are the outputs. The column here is the inputs, the column here is the outputs. So what's the domain of that relation? This group. And the range? Is that a function? Yeah. I don't have any repeating first ones, so it's a function. Doesn't matter that all of the second ones are the same number. That doesn't have anything to do with whether it's a function. We looked at something like this, and so that we said was not a function. But what about that? Would that be a function or not a function? It says draw a vertical line anywhere the function exists. Well, it doesn't exist here, here, or here, so don't draw it there. But anywhere I draw it along in here, it's only going to touch once, or anywhere I draw it along in here, it's only going to touch once. So that is a function. A function does not have to be one continuous line. It can have gaps. It's called a piecewise defined function. So you can have that situation and still be a function. So don't require that it be one continuous line. Notation for functions. Function notation uses a letter, a set of parentheses with a letter inside. Most commonly, F and X. This is stated as F of X. And from now on, if you see that type of a situation in this class, you can 99.9999% of the time you can consider that a function. I don't know that we're going to see any situation where that would not be a function. So letter, parenthesis, letter is function notation. In this function notation, this letter outside the parenthesis is the name of the function. This is the function f. The number that results for this is the value. That's the output of the function. Whatever value this has is the value of the function. The right-hand side is some kind of expression, mathematical expression of some kind. We're looking now just at polynomials. Later we'll look at some other types of functions. That's the defining expression. X, the letter that's inside the parenthesis and is also in the defining expression, that's the independent variable. So we talked about functions being independent variable, dependent variable. The independent variable is the X, the dependent variable is the function value. That's the dependent. That's the output. This is function notation. We're going to use it for a lot of places. And you need to be familiar with working with it and don't get confused. That is not f times x. It's f of x. One of the things you need to be able to do is to evaluate a function. Evaluating a function is just like evaluating an expression. You plug the numbers in. When you're evaluating a function, what you're going to do is you're going to be given a value for x, and you need to calculate what the value for f is, which means you plug the value for x into the right-hand side and do the calculations. For instance, if you're asked to find f of minus 1, that's the way you'd state it, f of minus 1, that means that if your function is defined this way, that looks just like we had on the previous page, f of x equals a defining expression. X is our independent variable, f is our function name. I want to evaluate this at the value x equals minus 1. The way you do that is by putting on the right-hand side, put the minus 1. Actually, we're going to write minus 1 in here also to show that that's actually what we're doing. So we're going to say f of minus 1 equals, then every place I have the variable, I'm going to put the value of minus 1. And then do the arithmetic here. So follow order of operations. And this is the value of the function f when it's evaluated at negative 1. So f of minus 1 equals minus 7. I could have said, what's f of 3? You could do the same sort of thing. Or f of minus 10, or any other number I want to put in there. And you do the same sort of arithmetic, you just do it with different numbers here. So the function f represents a whole bunch of different numbers. It's a way to identify a relationship between an input and an output. So evaluate this at minus 1, you get the number minus 7. We just did that. You can also evaluate these functions defined as sets of ordered pairs. In this case, we're going to define f to be this set of ordered pairs. I still want to evaluate f of minus 1. So let's first of all make sure this is a function. Is this a function? How do you check? First elements. Do I have a repeated first element? No. What does that mean? That it is a function. So because it's a function, I can plug a value in and I will get a unique value out. So if I want to evaluate this at minus 1, the way I evaluate a set of ordered pairs is I look to see where that is my first element. And if it's a function, there'll only be one place. So that's not it. Okay, there's minus 1. My value for f then is the second element. So I look here and I find minus 1 and then write this as my output for what f is equal to. So f of minus 1 equals 6 for that function. Yes? That's when you're looking whether it's domain, whether it is a function or not. So we did that. When we check whether this is a function, we don't have any repeated first elements, therefore it's a function. If there had been a repeated element, first element, then the second one would have to be the same in order to be a function. If it's not a function, we really can't do this sort of thing. Yeah, but what you're talking about is determining whether or not it is a function. As far as evaluating it, you have to have a function, or else evaluating it doesn't make much sense, because you don't know you don't know which answer to take on your output. So is this a function? This gets back to your question that you just asked. Is that a function? And it's not a function because we're repeated, but those are different. That makes it not a function. Now this one's a little bit harder to do. You might, probably when you're looking at something like that, because If we're saying x is our input, then we've got to try to figure out what y to the fourth looks like. And that one's a little harder. You actually probably would want to go ahead and do a rough graph of this and then figure it out. So it's easier to do a graph if we calculate y's, or select y's and calculate x's. So if I select 0, I'll get 0. If I select 1, I'll get 1. If I select 2, I'll get 16. If I select -1, I'll get 1. Select -2. And if you draw this, let me make sure I draw this right. Yeah, it's going to give you this. Like that graph we saw previously. It's like a parabola, but instead of being up or down, it's turned on its side. Actually, yeah, and this should be a +16, sorry. Because if I plug a y in, it's always going to give me a positive value for x. There's no way I can put a real number in for y and get a negative number for x. The only way I could do that is if I have imaginary numbers. Well, I looked at this equation and said, what's the easiest way to calculate pairs? When you're doing an XY table, you can pick either X and calculate Y, or pick Y and calculate X. It's not going to matter when you're making an XY table. Just make sure you calculate correctly. It's a lot easier for me to put a value here and take the fourth power to see what this is than to put a number here and try to calculate the fourth root. So put a number in here and raise it to a power rather than trying to take a root. But once I have it and draw the graph, then you can start looking and say, is there any way I can get a negative x? Actually, a fourth power is always going to be positive, whether it's a real number or an imaginary number. The fourth power, that's always going to be positive. So there's no way I can make x over here. So is that a function? No. How do you know? Vertical line test. Does it have a domain? Yeah. Even if it's not a function, it has domain and range. What's the domain? Domain is the x values. Where does this begin in x? So my domain begins at 0 and goes to where? Where does my range begin? Range is the y values. This actually, negative infinity to plus infinity. Because this keeps going down, this keeps going up. Just like on a parabola, it keeps opening outward this way. For this one, it keeps opening up and down. That's not a function, but it does have a domain and a range.